Alright, it's back to basics here in this particular video of the Advanced SQL course, because we are returning to the from clause of our select from where queries. And if the from clause isn't fundamental and basic, what would be? Okay, but there's quite some interesting observations to be made here and some confusion to be cleared up. And this video contains the answer to this. So it's not about the from clause per se, but it's even about this tiny symbol. It's about the comma in the from clause that we use to separate the tables over which we iterate in such a from clause. So in the sample from clause, we are iterating over the results of 3 queries Q1, Q2, and Q3. These might be tables, but as you know, they might also be more complex expressions, subqueries in parentheses that yield tables. And there were restrictions regarding the visibility of row variables. We said, and it's true, that the row variable T1 is not visible in Q2 and that T1 and T2 are not visible in Q3. I cannot look to the left of the comma here and access the row variables inside the subqueries. Okay, so that sounds strange maybe to some of you, because these commata, they suggest a left to right evaluation order. Okay, so let's first evaluate Q1, then iterate over all the rows, call them T1, and then evaluate Q2, iterate over all the rows, call them Q2, and then evaluate Q3 and so on. But it's not happening like this. The answer to this conundrum is that the comma in the from clause may suggest left to right evaluation, but indeed it's a commutative and associative operator. It allows the database systems to freely arrange these table clauses inside the from clause. So in the actual evaluation order, Q2 might come first and Q1 as last maybe. And if this is the case, then T1 is not bound yet when we evaluate Q2. I've depicted this down in the slide here. So if that would be the original order in the from clause and the original order that's suggested by the comma, you know that the semantics of all of this is that we indeed evaluate all the Q1, Q2, and Q3, find the rows, the set of rows, and build the Cartesian product. Build the Cartesian product of all possible combinations of the rows returned by the QI, and then evaluate the where clause, and then evaluate the select clause. That's why this time symbol, the Cartesian product symbol, is, I think, the appropriate symbol to denote what this from clause above in the slides actually denotes. And since it's like this, since we are actually talking about Cartesian products here, we might rearrange Q3 and Q2 and change their position in this Cartesian product. The resulting Cartesian product would still generate the same row combinations. Okay, we might still further jumble and shuffle the order of the QI and then maybe move Q3 to the front and Q1 second here. So that would be one order in which we could evaluate the QI. We could, as a database system, we could decide that Q3 and Q1 should be considered first because they are connected by some probably selective join predicate. So what we are computing here is indeed not a Cartesian product between Q3 and Q1, but a join. And we would hope that the selective predicate removes many of the rows of the intermediate result produced by this join. So we would end up with less rows, which are then fed into the Cartesian product with Q2 here. That would be a favorable order, and the database system is completely free in choosing that particular order, because the semantics of the comma is indeed Cartesian product, and we could rearrange and then make the order of the QI, and then maybe even introduce parentheses, so a particular specific evaluation order that considers pairs of these QI first, like in this parenthesized order. Because of this, the comma is really not a sequence operator. It's really something that's commutative and associative. And that's the reason behind the limited visibility of row variables inside these QI. Okay. But this dependent iteration inside the from clause is really super useful. We have used this many times already in many of the queries that we've specified in examples, and we've seen them live executed in the PostgreSQL shell. So there must be some form of dependent iteration inside PostgreSQL for sure. And that's the point of confusion that I was referring to. When we had such dependent iteration, it always looked like this until now. Okay, so this would be one of the queries over the array encoded trees that we've considered when we were talking about arrays. And if you look at this from clause closely, it uses dependent iteration. Dependent iteration meaning that one of the entries, this second entry in the from clause, this entry, is actually dependent on the row variable bindings introduced by this first part, by this first tabular subquery inside the from clause. So there is some dependency here from T1 to T1 here, and indeed T1 is visible in this query. It should be a problem. And regarding the slide that we've just seen, T1 should be not in scope inside this second tabular query or tabular entry in the from clause, but it is. And the reason is that there is an exception in the visibility of row variables in SQL. Tabular function, table generating functions or set generating functions like this honest function, they are indeed allowed to refer to row variables that have been introduced earlier. So T1 introduced here on the left, T1 immediately used on the right of the comma here. That's perfectly fine because we are dealing with a table generating or set returning function like honest in this case. We have seen this used to good measure in many of our example queries. For example, in the query that you just see on the slide, that finding the largest label, alphabetically spoken, the largest label inside each of the trees that we've represented here. But it's really an exception to the rule. The visibility of T1 is dependent on the fact that we are using it as in an argument of a set generating function. This has its uses and it leads to intuitive and nice compact query formulation, I would say. Okay. But such dependent operation would be useful in many other occasions, many other scenarios of query specification too. So this is limited to set generating functions, okay? But there is a possibility in modern SQL dialects to have such dependent iteration in regular from clauses too, where set returning functions do not play any role. We are just talking about a regular subqueries QI here. And this is where lateral comes into play. This is a SQL keyword that we have not seen before. And what it does is indeed, it introduces dependent iteration for everyone in the case, not only for set generating functions. All right. So with a lateral keyword prefixed to one particular tabular subquery QJ, we indicate that QJ is dependent on row variables that have been introduced to the left of this comma. Okay, so in QJ, we may refer to T1 and to T2 up to TJ minus 1. Of course, TJ is only introduced after we have evaluated QJ, but everything introduced before is indeed visible inside QJ. The scope extends from the left here up to the QJ here on the right. Okay, actually the keyword lateral is very well chosen because it has its origin in Latin, where it comes from the Latin lateralis, which means sideways. And that's, I think, a very reasonable and fortunately chosen name, because information is passed sideways from the left here of these first tabular subqueries on to the right sideways until we reach Qj, where we can access the earlier introduced row variables. Okay. So this is an explicit indicator, this lateral keyword. It's an explicit indicator that information is passed sideways from left to right. Okay. And I think it should be considered good style. It should be considered good style to also use the lateral keyword in situations where we are using set returning functions. Let's switch back one slide. I just told you that this reference to T1 here should be an error, but it isn't because of the exception that we are using set generating functions here. I think it should be considered good style to also use the lateral keyword in this situation, and you can actually do that. It would be syntactically valid to place a lateral keyword just here where I'm highlighting the slide right now, to explicitly indicate information is passed from left to right sideways. The row variable scope of T1 is actually extended sideways, and T1 is used here on the right of the comma. So from now on, I hope I can consistently remember and author my slides such that lateral is explicitly specified in my queries. If not, please complain in the forums. Okay, so this would be dependent iteration and sideways row scoping for any subquery, not only for set returning functions. What we then have here, I would say, is something like SQL's equivalent of an for each loop, of nested for each loops actually. Lateral is the way to specify a nested dependent iteration inside SQL. Okay, the query could look like this. Then we would have this from clause in which Q2 and Q3 explicitly announce that they would like to access row variables introduced on the left. So Q2 would indeed be a Q2 of T1. We might see 3 references of T1 inside the subquery Q2 here. Okay, I've tried to indicate this, or what happens here at the bottom of the slide. So we would start our evaluation with the iteration over the result of Q1. The rows of Q1 would be bound to T1. This is indicated here. And then, this is really a sequential and then we would evaluate Q2, which can now refer to T1 and bind the result to T2, the T2 variables. And then, once T1 and T2 are bound, the row variables are bound, we could use them in Q3, evaluate this subquery. If Q3 is a subquery, indeed T1 and T2 could be occurring in this subquery as 3 row variables. We could refer to these. We would find rows emitted by Q3 and would then finally iterate over these rows and bind them to T3. Okay. Now all 3 row variables are bound, and they would be usable in the select clause, E here. But it has always been like this. Any row variable introduced in the from clause, like T1 to T3 here, are visible in the where, and of course also the select clause. That's nothing new. This is the new stuff. T1 is usable in Q2. T1 and T2 is usable in Q3. This is real dependent nested iteration. I've just underlined that this is really a sequential evaluation of Q1 and then Q2 and then Q3. No other order would be possible in this case, and this might be very convenient and very intuitive, and it's also perfectly okay SQL, but you have to be aware that this is like handcuffs for the query optimizer. Rearrangements of Q3 and Q2 or Q1 and Q2, changing the order here, would now be impossible for the query optimizer. Lateral forces the evaluation order, and it might be suboptimal evaluation order that the system could optimize if you would remove the lateral keyword. Of course, then row scoping restrictions come into play again. So it's a trade-off. Let's quickly switch over to the editor where I brought such a dependent iteration queries with me. This is just the dependent iteration that is possible because we are using the unnest set generating function in this example. This is just the example from the slide. We introduce t here and can use it here, and that's only possible because unnest is a set generating function that constitutes an exception regarding the row scoping rules. We can evaluate that, I hope. Okay, so these are the largest labels in the 3 trees. But as I told you, I think it would be good style to explicitly announce that dependent iteration here and place the lateral keyword here, making the dependence of the argument of the unnest call explicit, dependence on t explicit. So let's evaluate that. That should work just as fine. So I think this is good style, the better style. If dependent iteration wouldn't be available, if dependent iteration would be forbidden actually inside PostgreSQL or inside SQL, then sometimes equivalent reformulations of queries would be possible. As we just said, the binding of t here is of course visible in the select clause, for example, and we could use that to equivalently reformulate the query above. In this particular fashion, we would just iterate over one table here in the from clause, bind the t. The t is visible in the select clause, so we could refer to it here. We could refer to it in this particular subquery. You see that the t is occurring free here. It would be visible because we are in the context of the select clause of the outer query block. And of course, we could invoke it here, and we could iterate over the results of the unnest function, find the maximum, and so on. All of this is possible having the subquery here because the result of the subquery is a scalar. This is a single column, single row table that is being returned here. So in this particular case, the rewrite from dependent iteration into nesting in the select clause was easily possible, but it might be more complicated if the subquery that we would need to specify here is not scalar. So we were in luck here and it should work just fine. But in general, lateral might be a viable solution to introduce dependent iteration that is not easily rewritten into such nested queries in the where or select clauses, for example. Okay. I brought one example with me here, a lateral example that is representative of many users of lateral out there. Let's see what are we trying to do here. So we are looping back to our table of dinosaurs that we have seen in earlier videos and earlier chapters of our course. Okay, so what we are trying to do is we find the 3 tallest 2- and 4-legged dinosaurs. So in the result, we would expect 6 rows. The 3 tallest 2 and the 3 tallest 4-legged dinosaurs. And indeed, that's what you can see here in the result. We are talking about 3 2-legged and 3 4-legged dinosaurs. And these are indeed the tallest species if you would check the entire dinosaurs table. Okay, and one, I think, very natural way, one intuitive way, one elegant way, you might say, of specifying this query is using this tiny embedded literal table that just contains the 2 and the 4. So locomotion.lags will be bound to 2 different values, to the value 2 and the value 4. For each of these 2 values, we would evaluate this query. Okay, and the wording I've just used, for each of the 2 values 2 and 4, we would evaluate this query, already implies this dependent iteration, the sequential evaluation, that this part of the from clause is evaluated first before we then have a bindings for locomotion.lags, which we can use here in the second subquery. And you can see indicated by the arrow here, we are indeed using it. So this is the free row variable reference inside this subquery here, but it's perfectly okay because of the lateral. All right. So this would be either 2 or 4. So if it's 2, then we would restrict the dinosaurs to the 2-legged dinosaurs. We would just order them by height, take the 3 largest dinosaurs and return them. It's super simple, very straightforward. In the second iteration of this subquery, locomotion.legs would be 4, and we would do the same operation for the 4-legged dinosaurs. Each of these subqueries would yield 3 rows each, at most 3 rows each, let's say. And this would be the overall final result. So it's indeed nested iteration. The outer loop and the inner loop in a sense. Okay, so let's switch over to the terminal and see this in action. Okay, so here's the query. This is just verbatim the query that we've just specified over on the slide. Here you see the free variable reference, and of course you see the use of the lateral keyword that makes all of this possible. So let's see. Yes. Okay, so we see the same result, just the result we have seen on the slides. And you see that the query will break down once I remove the lateral keyword here. So let's beautify this again. Now the lateral is missing. Now this should be an invalid reference. Now this is a really commutative comma again, and the system would in principle be free to rearrange the duration of this subquery and this subquery. So we could not rely on locomotion.legs to be visible and usable. And indeed the system complains. It complains exactly at the reference of locomotion.legs in the second subquery. There is some table locomotions, but you cannot reference it from this part of the query. Yes, indeed, without lateral that's not possible. So let's reinstate the lateral here. And everything's fine again. Recall that earlier we have rewritten the very simple query that was looking for the largest labels in trees, and where we moved the evaluation of this particular query and moved it into the select clause to get rid of dependent iteration and make the locomotion.legs variable reference valid. It's not so easy in this case, but because this is not a scalar subquery, it will return more than one row in general, and it will return more than one column in general. This is not a scalar subquery. So the easy trick of just moving this stuff into the select clause in some way or fashion would not be possible. We could rewrite this query without dependent iteration and still compute the same result, but this rewrite would be somewhat more complicated. I brought the rewrite with me. You see, let's make this a bit larger. The query is a bit larger now. And if I would have to choose between this particular formulation, which does the same as this formulation, I think I know what choice I would make. This reads more compactly and more readable, I would say, than this. So let's quickly look at what's happening here. So this introduces a ranked dinosaurs table that looks just like the normal dinosaurs table. Actually, I think we are omitting the length column here because it's not relevant. But we are introducing a new column rank here. A new column rank that ranks the dinosaurs regarding their height. Okay, so we are ranking dinosaurs regarding their height. We would iterate over all the dinosaurs which have some defined leg number, because as you recall, we would separate the 2-legged and the 4-legged dinosaurs. Okay. Okay, so we would grab one of these dinosaurs, D1, and then inside the select clause here, okay, we would be able to refer to D1. That's fine. No dependent iteration, but the visibility of D1 is just okay in the select clause, no problem. Okay, so given a dinosaur D1, we would iterate over all the dinosaurs D2 again. Of course, only the same legged dinosaurs. We would not compare apples with oranges here. Only 2-legged or only 4-legged dinosaurs would be compared to each other. And we would try to count how many dinosaurs D2 are actually larger or have a taller height than our dinosaur D1, and that would define the rank of our dinosaur D1. The more the the more dinosaurs D2 we can find that are taller than ours, the larger would be the rank of our dinosaur T1. It would be sorted later in the ranking order, in the height ranking order of all the dinosaurs. Okay, so that's what we would get. We would get a 4-column table, the ranked dinosaurs table, in which the rank specifies a rank 1 specifies, for example, that we are the tallest dinosaurs in our peer group, in our lag peer group. Let's see what the let's comment this. Okay, so let's see what this intermediate results looks like. Okay. So this would be all the dinosaurs with some defined lags. Okay, okay, lag number, and you would see that we have assigned a rank here. So inside the group of the 2-legged dinosaurs, the Tyrannosaurus with its height 7 would indeed be rank 1. There is no taller dinosaur in the two-legged group. And the Velociraptor of height 0.6 would be in rank 7. It would be ranked lowest here. Okay. So, and the same, of course, is being done for the 4-legged dinosaurs. That would be the intermediate result that we get when we are looked at the ranked dinosaurs table. Oh, quite complicated already, huh? You've seen me hesitating while I was trying to explain the logic of this query. I was looking at this predicate and try to decode its semantics. It's really something to look at here and try to understand. Okay, so let's remove this again. Okay, given these ranked dinosaurs, we would then check that the rank that we are looking at is indeed among the top 3, and that would be an indicator that this is a dinosaur that we indeed want to put into the result. And just to make this more readable, we would order by legs so that the 2 and the 4-legged dinosaurs are separated in the output, and then by rank so that the tallest dinosaur comes first. All right. So if we evaluate this again, then that's what you see here. Tyrannosaurus comes first. Spinosaurus qualifies as 3rd in this particular output. Okay, and that should be the same output that we have seen with the dependent iteration query. So this is just some query. It's not too super complicated, but it's more complicated to grasp and to explain as this dependent iteration one. So the dependent iteration has its uses, and we will use it to good measure in the specification of more complex queries, and that's fine. But please be aware that it's like, as I told you, handcuffs for the optimizer. The lateral turns this comma into something else, from a commutative Cartesian product into a real sequential or a real sequencing operator. That's fine if you are aware of the performance consequences. All right. Thanks for your attention. See you around. Bye.